Hi there, this is Math 8, and today we're looking at a review of Unit 2, Lesson 10. We're introducing ourselves to our good old friend slope. Meet slope today. And we're going to talk about the slope of a line as we go through this lesson today. So looking at part 2 you worked on first today. It says similar triangles on the same line. The figure shows three right triangles, each with its long side on the same line. So you were going to be assigned two triangles to take a look at by your teacher and talk about how they were similar to one another. Okay? So just for the sake of what we're doing here, because I'm going to look at all of them, this is kind of recap in case you missed a lesson today. The vertical side of length ABC is right here at 3 and the horizontal length is 4. If I divide the vertical by the horizontal, I have 3/4 is that ratio there. The quotient of the vertical and the horizontal is 3/4. For CDE, this one here, the vertical side is 6, the horizontal side is 1, 2, 3, 4, 5, 6, 7, 8. And so the vertical over the horizontal is going to be 6/8, which is also 3/4. And FGH, we have a vertical of 1.5, 1.5, and horizontal of 2. And so 1.5/2 there. But if I multiply both this by a scale factor of 2, just so we can help ourselves out here, I end up with 3/4. And so what we see here in our little example with these triangles, these three triangles at right angles that share the long side together, is that the quotient of the vertical and the horizontal is equal. We call this quotient our slope. Okay? And that's what today's lesson is about. We take these triangles we've done before, so we've done some translations as we move them around and dilations to slide them on top of each other. What we're seeing overall is that I can do that same thing and start to compare this slope or this measurement here of how this line is going up. Okay, so the next part, in part 3, you were to draw two lines with a slope of 3. Okay, so to do that, you might have plotted a point, let's just say right here, and a slope of 3 means I'm going to go up 3 and to the right 1. So we're going to go 1, 2, 3 and over 1, 1, 2, 3 and over 1. There's 1. Maybe I start here and I go 1, 2, 3 over 1, 1, 2, 3 over 1. Now if I just drew a quick line there to connect those dots, what I'm going to notice is there's one line, and let's see if we get this one there. Pretty good. There's another line there. We'd say those two lines look to be fairly parallel, don't they? Okay, I mean they're going the same direction. Granted, my lines aren't perfect, but it's pretty close. For the next one, if we looked at a slope of 1 to 2, right? Let's say we're in a starting point here. We're going to go up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. I might have one line here looking like this one. That's one line. And if I did another line starting, let's just go ahead and start here. Up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2 for the 1 over 2 slope, or half slope. We're there. And so now I have another set of parallel lines. So when the slope was the same, our lines are going to be going in that same direction or have the same slope. That's what a slope does, is it causes that line to go the same direction, the same kind of tilt you might want to say there, however you want to think about it. That's the idea. So when we look at the next one, it says here are several lines that have different slopes because they're different lines. Match each line with a slope from its list. We have a third, 2, 1, 0.25, 3 over 2, and 1 over 2. So let's take a look here how you might do this one. If I was going to solve this, what I might consider doing would be going, well, this one's going to go up 1, 2, 3, going up 3, and we're going to go over 1, 2. So this becomes a 3 over 2, 3 halves. Write that nicer for you. Apologize there. 3 over 2. So we can check that one off. Got it. This one is going to be, you think about where we're going, make my lines connect. I'm going to kind of fill in the box. I'm going to go up 2, there's my 2, And I'm going to go over 1, 2, 3, 4, 5, 6. Up 2 over 6, which reduces to 1/3. And that's a choice there. For this guy, we're going to end up going here to here. So we're going to go up 1, 2, 3, 4, 5, going up 5. We're going to go over 1, 2, 3, 4, 5, over 5, which becomes a slope of 1. Here, I'm going to pick a point. There's a point where it crosses. Here's a point where it crosses. Here's a point where it crosses. And I'm just going to take a look. We're going to go up 2, and over 1. So my slope in this case becomes simply 2. For B, we have a point there, and it looks like we're crossing there, and we're crossing there. So I could draw a little triangle here if I chose to. And it looks like we're going up 1 and over 1, 2, 3, 4. So we have a slope of 1/4. I don't see it as a choice. Oh no, that's okay because 1/4 as a decimal is 0.25. Okay? It says one of the given slopes does not have a line to match. Draw a line with this slope on the empty grid. So we want to draw the one for 1/2. So if I start here, okay, I'm going to go, this is my vertical, up 1, and this is my left right. I'm going to go up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, and up 1 over 2. And that's where my line is going to go through that point right there. And again, if I connect my dots up, I end up with a line looking something like that. And that's what that one is going to look like. So we're just taking a look at how this slope works. It's the amount, it's a quotient between the vertical and the horizontal. It's the quotient between the vertical and horizontal, vertical, horizontal, vertical, horizontal. Again and again, it's how we figure out what a slope is going to be. So in summary, right, what we're talking about is how we can compare slopes. And it's that vertical over the horizontal again and again and again. Okay, so whether it's up here and we're looking at, well, in this case, I have a 4, for this line, 4 over 6. This slope looks like 4 over 6, which is the same as 2/3, right? We're in good shape there. Here, I'm going up 2 and over 3. So again, it's a 2/3. In this case, I have 2/3 over 1. 2/3 over 1 is also 2/3. Those are all going to be the same, have the same slope. These are going to be similar triangles because they have the same slope, and they're going to have a lot of similar angles there. Okay, so slope works that way. Okay, and that's what we find out is that's just how it works there. So the slope of the line is the quotient. Here's your key thing here. The slope of the line is the quotient of the length of the vertical side and the length of the horizontal side of the slope triangle. And that's true for all slopes as you work this out. Okay? And even if you were to flip it upside down, like this one here is flipped upside down, you go, oh no, what am I going to do? Well, we're going up 4 and over 6. It's still 2/3. Even though the triangles change the other direction, you still end up with the same slope for that line right there. Alright, so make sure you start your homework and then press pause and come back and let's take a look at it in just a second. Okay, so here is lesson 10 homework on meet slope. Of the 3 lines in the graph, one has a slope of 1, one a slope of 2, and one 1/5. Label each one, and here we go. So let's take a look at the first one. This one we're going up 1, over 1, up 1, over 1. We're going there. Our boxes is simply a 1 to 1. So this one here would be our slope equals 1 on this guy right there. For this one, we start here, and I can see I'm not crossing a point until right about there, right? So in this case, we're going to go up 1, 2, 3, 4, and over 2. We're going up 4 and over 2, which equals 2. So this one has a slope of 2 on that one. On this guy, I can pick any point I want. I can go point there, and I have a point there. We're going up 1 and over 1, 2, 3, 4, 5. So 1/5 there. So this slope equals 1/5. Okay? And so the different slope is going to change the angle at which that line goes up or down, whatever it might be. Next one, number 2, draw 3 lines with slope of 2 and then 3 lines with slope of 1/3. Okay, well, here we go. Slope of 2, we will just start right here. Slope of 2 means up 2 over 1, up 2 over 1. I'll start one over here. Here's 1, up 2 over 1, up 2 over 1, up 2 over 1. And you can put as many points as you want. It doesn't really matter. It's up to you. You just have to eventually connect the dots with your ruler. So if we draw this out, we're going to have a line here. I'm going to have a line here. I'm going to have a line here. Not very nice lines, just kind of sketching through your homework there. And we end up with 3 lines that are parallel. If I did the 1/3 part, and let's just say I start here, I'm going to go up 1 over 3, up 1 over 3, up 1 over 3, and we end up with a line that looks like this. Probably better to use ruler, right? Do another one. Here's 1 over 1, 2, 3, up 1 over 3, up 1 over 3, and so we end up with a line like so. And another one, I could start here, 1 over 3, 1 over 3, and we connect the dots there. So now I have 3 parallel lines this way and 3 parallel lines that way. Okay, so that's just what I noticed, is that every time the slope is the same, I end up with parallel lines. Next one, the figure shows 2 right triangles, each with its longest side on the same line, which is what we've been looking at here. Same line, same line, same line. Looks great. Okay, how do you know the triangles are similar? Well, we know it's similar because we can translate r to x, right? We could translate it and move it right there. If we were to translate it, we would say it's 1, 2, 3, 4, and 2. It would fit right here in this space if we want to do that. So if I translated it and moved there to there, that becomes a 4 and a 2. This becomes r prime, s prime, t prime. With a translation and a dilation, I can prove that they're similar because they're going to have a common angle there. They're going to have common angles here as well. And so we know they're going to be similar there because of that. Now, question is, how long is xy? Now, xy is this length here. We can measure it, 1, 2, 3, 4, 5, 6. That's handy. But we could also look and see, well, how do I get from there to there? Again, this is just a dilation, right? If this was 4, and I do 4 times the scale factor, gives me my answer I'm looking for there, well, that's what I'm trying to solve. I just call it x there. Let's call it xy, length xy. I do know this one. I know that TS is 2 times the scale factor gave me 3. So what's my scale factor going to be? Divide by 2, divide by 2. My scale factor is 3 over 2. So now if I do 4 times 3 over 2, I end up with 12 over 2, which equals 6. So that's how I can prove that that is the answer rather than just count the 6 squares. For each triangle, calculate the vertical side divided by the horizontal side. So in this first one, our vertical is 2 and our horizontal is 4, so that is equal to a half. And here, our vertical is 3 and our horizontal is 6, which is also equal to a half. So the slope of each line is going to be 1 over 2, or a half. And we know that's true because we could plot it in, do it again and again. 1, 2, 1, 2. Here we have 1, 2, 1, 2, 1, 2. We always end up with a point on that line each time we do that process again and again. Looking at number 4. This is triangle A has side lengths 3, 4, 5. B has lengths of 6, 7, and 8. How do you know that B is not similar to A? Again, the point is that if these things are similar, okay, I should be able to take a number times a scale factor and end up with the other one. So 3 times the scale factor should equal 6, right? And in the same way, 4 times the same scale factor should equal 7. If I use, for example, 2, 3 times 2 is 6. That's true. But is 4 times 2 8? We would say, no, it's not. Yes, it is 8. It's not 7 is what I meant to say. And since it doesn't equal 8, this is how we know these triangles are not similar. The scale factor needs to be the same for all the corresponding lengths in order for that to be true. give a possible side length for triangle B so that it is similar? Well, to do that, if we had our original lengths of 3, 4, and 5, if I did a scale factor times 2, times 2, times 2, a similar triangle could be of length 6, 8, and 10. As long as you multiply by the same scale factor for all three values, you're going to come up with three sides that are going to be similar to the original one. Okay? And that's all for tonight's homework. Hope you have a great night. See you next time.